Assalamualaikum to our lecturer, Dr. Muhammad Ibrahim, and my fellow friends. We are from Group B. We present about copper hexacyanoferrate 2 complex. We are uh, NURHAFIZA, Sofea, Hani, and me, SITI, NURHAFIZA. Now we will move to introduction of the compound. Okay, the introduction of the compound. The compound consists the transition metal, which is ion 2, bond to the cis ligand, which is cyanide ligand. The color produced is the dark brown color. So we will proceed to method of synthesis. Potassium hexacyanidofferrate 3 aqueous solution and copper chloride was mixed together in a conical flask, and then the mixture was irrigated with a high ultrasound radiation about 50 minutes, and then the resulting solution deanalyzed to eliminate ion excess, and the stable dark color solution will form. After that, the powder form obtained by the centrifugation was washing by water, and then the remaining solution that produced will be removed, and the solid obtained will be dry at a low pressure and at room temperature. For the last step is, after we keep for 5 minutes, we wash again with water and then dry it with N2. Now we move to the point group determination by NURHAFIZA.
So for the point group determination, hexacyanoferrate 2 has an octahedral point group. So next. So these are all the symmetry elements operation of the hexacyanoferrate 2. It has 10 of all for the total of the operation. Next. From the left, it has, of course, it has identity and inversion center. Also, for the N4 rotation, starting with a C2, C3, T4, and 6C2 prime N4 rotation. For the improper rotation, it has, from the right side, it has one of the 3s4 axis, one of 4s6 axis. For the mirror planes, it has one of 3 sigma H mirror plane and one of 6 sigma D mirror plane. Next. So for the charge, determine the point group. The molecule is not linear. It has more than 2 CN axis. It has center of inversion. It doesn't have a C5 axis, so therefore it's an octahedral point group. So next. For the type of ligand bonded for crystal field theory, focus on a 5d orbital. With the ligand arranged in the regular array around a transition metal, the dz square and dx minus y square orbital point directly at the sig negative charge located at the x, y, and z axis. The energy of an electron on these two orbital label will be greater than it will be for the spherical distribution of negative charge because of increased electrostatic repulsion. I will explain it later. The other three d orbital, dxy, dxz, and dyz are oriented at 45-degree angle to the coordinate axis. The energy of an electron in any of these three orbitals is lower than the energy of spherical distribution of negative charge. So next. From the left of the diagram, we can see that the two of the EG orbital point directly at the 6 negatively charged ligand. So the energy is increased as the electrostatic force between the cation and anion metal and ligand closer, so the repulsion becomes stronger. For the right diagram, the 2G orbital point between the negatively charged ligand, which decrease the energy compared with a spherical distribution of charge. Next. For the ligand field theory, the dx minus y squared and dz squared orbital lie along the bond axis. The orbital rates relatively high in energy. Orbital like anti-bonding levels. Dxy, dxz, and dyz orbital lie between the bond axis. And the three orbital will change in energy only a little. These orbitals are more likely non-bonding orbital. This orbital is sometimes called the T2J self-orbital. Next. So as we know, Fe2 has 3d6 for the Dn configuration. And if you use Cn for the ligand, Cn is a strong field ligand, also is a low spin configuration. Therefore, the d orbital splitting energy is too high. The next electron must pair up in a lower orbital since the energy is higher. All three remaining electrons pair up in the lower energy. So next.
So now I will talk about the spectra related to the compound. The diagram it shows around 4 spectra, but we will only focus on the FTIR and the UV rays. So each spectra has two lines, the red and the blue ones, because from the research paper it contrasts between the complex with the transition metal ion Fe2 plus and Fe3 plus. So for the FTIR, we will focus on the red peak, which is the Fe2 plus peak. So the high intensity is because of the metal ligand bonding interaction. So uh, there is a shift of the peak because due to the higher oxidation state of the Fe3 plus, it lowers the energy at the metal ligand bonding, hence the intensity. And these peaks, the first peak, which is the red peak, can be found at the 2037.6 wave number, and this second peak can be found at the 77.6 with number shift with the at about 3 times decrease in intensity. So next is the UV ray spectrum. Here it shows the electron volt for the x-axis. We can convert the value to the wavelength using this conversion values. So I will only focus on the red one because this is the Fe2 plus spectrum. So the first feature is at the 3.67 and 4.71 electron volt that corresponds to the DD transitions of the metal that mix with the ligands S and P orbitals and the surrounding solvent orbitals. Then there is a large increase in the peak at 5.31 electron volt, which is composed of metal to ligand transitions, because metal to ligand transition is when the electron moves from the metal orbital to the anti-bonding of the ligand orbital of the anti-bonding ligand orbital. So there is a very high energy. So next is the magnetic properties. Uh, as what FAZLINA has said, because the DN configuration is D6, we have 6 valence electrons, and having the cyanide ligands, there are strong ligands, it causes the crystal phase splitting energy to be higher than the pair energy. So the electrons tend to pair in the lower orbital first, and when all the electrons are paired, it is called a diamagnetic property. Next, I will give back to FAZLINA for the geometry.
For the geometry of the hexagonal 2, it is symmetrically assigned by the 6th atom of Cn. It has distinct octahedral shape. For the bond angle, the Cn and Cn side by side, it has 90 degree. For the 180 degree, it is opposite of the ligand. Cn and Cn opposite, it has 180 degree. So that's all for the geometry.
Now we will move to the last part of our presentation, which is the application of the compound. First, the first application is for film ion by film modified electrode. It's used in chemistry and material science to the area of electroanalysis and chemical sensing and electron catalysis. in study of interfacial charge in ion exchange and electron transport. The method used for this application is electrochemistry technique. Second part of application is as cesium absorber. The capacity of absorber of CHCF2 was determined by the batch experiment as a function of cesium concentration. Its distribution between solution and solid was determined at approximately 25 by analyzing the former. Capturing dissolved ammonia is the last application for the compound, which is fast absorption kinetic and least impact of coexisting sodium ion in the abundant environment of water. The suitable pH for constant absorption is around 2 to 7 pH. That's all for application of the compound. And this is the last part. This is our reference and our reference for the research in copper hexacyanoferrate 2 compound. That's all from us. Thank you.